It's my great pleasure to introduce Moti Segev. Moti Segev is a distinguished professor and the Trudy Norman Lewis Professor of Physics at the Technion. He received his BSc and Doctor of Science degree from the Technion in 1985 and 1990, respectively. Spent 1 year in Caltech as a postdoc, then as a senior research fellow. Then he joined Princeton in 1994 as an assistant professor. I don't know if you remember or not, but I came to visit you in Princeton, and that's where I first knew you, in Princeton at about that time. I don't know exactly, but you stayed there until 1998, so it was between 1994 or 94 and 98. So I've followed his work since and met him periodically, and so it's great to have him in Ottawa. He returned to Israel in 1998, and in 2009 he was appointed distinguished professor, as I mentioned before. Actually, quite a compliment at the Technion. It's a major university, as everyone knows, but more than that, there are only 5 other professors who are distinguished professors at the Technion. So it's quite an accomplishment. He's a fellow of the Optical Society of America, the American Physical Society. He's been awarded prizes, the Quantum Electronic Prize of the European Physical Society, for example, the Max Born Prize from the award from the Optical Society of America, the 2014 Arthur Schawlow Award of the APS, and well, he's a major player in nonlinear optics. I could try to summarize all the different places, but I think, again, like the last speaker, I will let him speak for himself, and he's going to talk about Photonic Topological Insulators. Thank you.
Thank you, Paul, and Sylvain, and Bob for inviting me. So in the context of what Serge Roche told us this morning about mergence or coming to photonics and solid-state physics coming together, this will be the spirit of what I'll be talking about today. And when you go to do experiments that are relevant or inspired by solid-state physics, you need to come to think actually why you do this kind of experiments. And the reason is, there is a deep reason to this. The deep reason is that in optics, you can actually isolate the effects much simpler than in condensed matter physics. You can pinpoint exactly what you see, you can test your understanding, and you can inspire new ideas that sometimes years after are being rediscovered in solid-state physics. So what I will show you today was inspired by a discovery in solid-state physics, and later on it made a series of discoveries that we made, and at least 1 or 2 of them already were confirmed about 18 months after us in solid state and in cold atoms. So it is nice to see how these fields are getting together. So what I'm going to talk about today is about a new field that started, I think, fair to say, around 2009, not by me, but my former student, Marin Soljacic, and this field is now called topological photonics. And I think it will have a major impact, not only on optics, but also beyond optics. Already the cold atoms people are right there and there are many other fields, including exciton, polariton condensates already in, and quite a few others. So the work was done by several very talented people. The first one is Michael Rechtsman. He's Canadian from Toronto, and he wanted to be a professor in Toronto. He had 8 offers, but none from Canada. So the offers that he had one of them was Cambridge in the UK, and Purdue and Georgia Tech, and various other good schools. But because, how do you say in French, chercher la femme? He went to Penn State. His wife is a professor there. I'm still upset with him that he went there because I think he should have gone to a better place. But I wish him luck. He just started. Many of the ideas here that you will see, including how to realize the system, were generated by Jonathan Plotnik, an excellent student that is graduating these days and is in the industry, and I'm trying how to persuade him to go for a postdoc. I'm not sure that I will succeed, but I will try. I'm still trying. And the third one is Alex Zamait, my German scientific son, who is a junior professor in Jena in Germany, excellent guy. If you look at his record, you will see that he can easily get jobs outside, but he wants to raise his children in Germany. So let's see, junior professor is a tricky position in Germany. Other than them, those of you that know that you know what exactly I'm talking about, if you ask yourself why Ketterle is not in Germany, that's one of the reasons. because he didn't get offers when he was very young. Offers as an assistant professor. At that time, there was no assistant professor. Okay, so other than that, the work here was done by quite a few others. My postdoc, Miguel Bandres, who did his PhD in superstring theory at Caltech, and I pulled him out of that, and I convinced him that it's about time that he will do some physics, theory or experiments of something that can be measured within his lifetime. And he is happy, and actually it turned out to be excellent, not only excellent theoreticians, but also excellent experimentalists. Kobe Loomer, that is about to graduate in about a year, and two of Alex's students, Julia Zoyner and Simon Stratton. And that's our paper that was the first photonic topological insulator. And let's go now to the physics of that. So I think it is fair to say that if you 2 days ago was the Nobel Prize, the Physics Nobel announced. I was hoping that maybe there will be a big celebration here, but it will have to wait for a few years. It will come. But I think that when you think about the areas in solid-state physics and the contenders for the Nobel Prize, in condensed matter specifically, there's only one, only the topological insulators. There's nothing else. Why? Because the other discovery that was made in solid-state physics is Majorana fermions by two groups, one in Israel and one in Netherlands, and they were both discredited for now at least, or not, maybe not discredited, but there are other explanations. So Majorana fermions have not been observed as it stands today. So the only discovery, real discovery that is major and that is worth a Nobel is the topological insulators. And they were proposed for the first time by Charlie Kane in a seminal paper in 2005. Then came another theory paper by Bernvik, and the first experiment was done in Germany by the group of Molenkamp at Würzburg. So the idea, there are many ways to discuss this, and some of them rely heavily on mathematics. So I'll try to deliver the message, convey the message on the fingertips, okay? So let's suppose, so what are topological insulators? Let's suppose that you have a system that is two-dimensional, just to make it simple, okay? So topological insulator is an ideal insulator in the bulk, but it conducts electricity on the surface only, on the perimeter. Now, the conduction of electricity there, it's really like a supercurrent. It means that it goes into one direction only, and if you put defects, or if you put some shapes of the surfaces, it is completely idle to them. In other words, it will continue like in perpetual motion around the perimeter in one direction. So if you put scatterers or defects or sharp corners or whatever, it never scatters into the bulk and it never scatters back. This is the idea of a topological insulator. Okay? And the same if you think about 3D. So now you have a surface, where the surface, not only a perimeter, but the surface that will do the same thing. That's the idea. So why does it happen? It happens because of some very interesting property that is unusual. Okay? So let's think what happens if there is scattering. So let's say that I have some scattering potential, and I have a wave coming. So what we usually have, some of that is transmitted, and some of that is back reflected. So those of you that do nonlinear optics, they know that there are some particular potentials that are reflectionless, and solitons happen to have a particular potential like this. I can tell you from the book of your PhD advisor, of Cohen Tanuji, that hyperbolic secant square is a reflectionless potential, but it is sensitive to the ratio between the wavelength and the height and the amplitude, okay? But this is something that is completely not sensitive to anything. So what happens here is actually the wave or that current, the current or the wave packet of the electrons goes around the perimeter, and it is never scattered back, in spite of having something that should have scattered back. Why does it happen? It happens because there are no states to scatter into. In other words, the density of states to scatter backwards is 0. If your system does not have, if you don't flip spin for fermions. So there is no way it can scatter here backwards because there is no state to scatter into. That's the idea. So let's explain it in another way. Let us look first at an insulator. So we have valence band and conduction band, let's say square lattice for the sake of the discussion, and there's a band gap there. Now what happens now if you put magnetic field, where this was discovered by von Klitzig, who won the Nobel Prize, and what happens now is that for particular flux, the magnetic field here will make the electron precess. And if you look at any given point right here in the bulk, you see that the current or the precession of the electrons cancels out. There's current in this direction, and then from the other side, there's current in this direction. They exactly cancel out. The only one place that they don't cancel out is on the surface, on the interface, because here it's missing those precessions outside. So what happens now is, according to the spin and the direction of the magnetic field, it will only go in one direction. Okay? If you look at the dispersion curve, what happens now is that now you'll have the surface states cross over from one band to another, and they cross. They don't go straight, they cross in this form. Okay? So that can explain a little bit why there's no scattering. Why? Because what happens now, if you're looking at the surface state, at those states that go here on the perimeter, and you sit right here, let's say, near the Fermi energy, now if you have some defect that has some potential that is not huge, so it cannot cross the band gap, you have to remain within the band gap. It cannot couple to this band, it cannot couple to this band. So in other words, it cannot couple to the Bloch modes of the bulk at all, because the gap is large. Okay? The only way it can do it if there is a huge defect that will couple from here into the band. But as long as the gap is large, it will not do it. Okay? And why does it have directionality? Because the gradient, or there is a slope here, a non-zero slope. So you have a gradient go around and around. So this discovery today, the idea of topological insulators was expanded, or the concept was expanded such that it includes also the quantum Hall effect. But what Charlie Kane proposed and Duncan Haldane is that this can happen also without magnetic field at all, by virtue of spin-orbit coupling. This is the modern topological insulators. So what you have is the dispersion curves look exactly the same, okay, with these surface states crossing the band gap, and the spin-orbit interaction gives rise to unidirectional current that is topologically protected. For that particular spin, let's say spin up, it will have to go only in this direction, and if you want to scatter backwards, you'll need to flip spin. So a magnetic defect will flip spin and will go backwards, but as long as your system does not contain magnetic defects, you'll have a perpetual current that will go only on the surface, and it cannot couple into the bands because there is a band gap and the surface states are right here in the gap. Okay? So that's the idea on an intuitive level. So what do we need to do to have a topological insulator? We need to have edge conductance only, and it needs to be immune to scattering and defects. In other words, there's no backscattering and no scattering to the bulk. For the quantum Hall effect, what does the job is a magnetic field. But for topological insulators in the modern ones that were discovered in 2006, you need strong spin-orbit coupling, or something that will play the same role. So as soon as this came out, Duncan Haldane from Princeton was thinking for quite some time about a photonic realization of the same idea. Now, there's a fundamental difference between what happens for electrons and what happens for photons. The fundamental difference lies in the fact that photons are bosons. So you cannot have this kind of spin-orbit coupling in the way that you have so naturally for electrons. So you need to find something else. And also, they are not amenable to magnetic field in the usual sense. You put some DC magnetic field on light, nothing happens. So what to do? So Duncan Haldane actually proposed, he wrote a very mathematical paper that proposed a model that he said maybe one day it will be implemented in photonics. But he didn't have any idea how to do it, and the one that picked up on that, and on that idea and had an idea how to do it, is my former student Marin Soljacic, and he wrote a theory paper here on proposed how to do it, and then a year later he had a paper in Nature demonstrating the first one in microwaves. Now so you need something that will work with magnetic fields. So actually at that time, what they wanted to do is the equivalent of the quantum Hall effect. It requires a strong DC magnetic field. So what you need for that, you need something that is some material that responds to magnetic fields, and the response needs to be very strong. So he went to microwaves and he created a photonic crystal in the microwave. You see that's a photonic crystal. The lattice constant is 4 centimeters. Each one of these rods is a gyro-optic material, so that when you put on that magnetic field, you break time reversal symmetry. And what they saw is that they put a wedge right here, so it's like a defect, and the current went around the defect and so forth. And you can see from here, when there's no defect, current goes one direction. Current here is really an electromagnetic wave in the microwave. And then there is a defect with this wedge, and the wave packet goes around it, and it goes around, continues to go around it without being backscattered. That was the 2009 paper. So this is very nice, but it's not photonics, and it's not really, it's the equivalent of the quantum Hall effect, and it cannot be carried over to the photonic regime, in other words, to frequencies that are terahertz and higher, simply because magnetic response is extremely weak and cannot do the job. So you need to find some other trick. And I should tell you that in optics, actually, this idea is important not only for fundamental physics, but also it's important for applications. Why is that? Because one of the major obstacles that there is today in optical telecommunication is back reflections. So the way that in optical telecom we solve the problem is by taking magneto-optic material and making a Faraday isolator that employs magnetic fields, and you put them there in the system. So it used to be quite big when I was a student. Today it's on the order of 1 millimeter. So it's smaller and the materials are better, but they still cannot be integrated on a chip with any optical material. These are materials that are different, fundamentally different. So there is a drive, there is really motivation from the applications point of view in optics to try to find some other trick that could avoid backscattering and back reflection. Okay? So there is need for that in optics, in real applications. So what we really need now when we want to bring these ideas of topological insulators and bring the idea into optics, into the optical domain, or let's say terahertz and higher, we need to have some kind of a conceptual leap that is similar to what Kane and Milley did in 2006. In other words, we need to have something that makes a jump from the quantum Hall effect to the topological insulator. But we don't have spin-orbit coupling in the way that fermions have, like electrons have. So what to do? So there were several theoretical propositions. Some of them are more credible, some of them are less physical. So there is one of them by Carusoto in about circuit QED-based photonic lattices, has not been realized as of yet. There is an important one, actually. This is the one that is listed here, number 2, by the group of Misha Lukin. Actually, this is a theory paper that was submitted to Nature Physics, and it has conflicting reviews. It came to me for review. And I told them, look, guys, you have to, I think the idea is conceptual and it's important, but you need to rewrite the paper because nobody in the photonics area will be able to understand what you guys are talking about. That's number 1. Number 2, I said that in my opinion, it's unlikely that it will be fabricated within the next few years, but because it's conceptual, I think it should be accepted. So the editor accepted my opinion. He let that concept paper be published, and after they rewrote a good part of that. But to my great surprise, actually 6 months after us, they had a paper appeared in Nature Photonics that has shown a topological insulator in photonics as well. So they published that in November or December of 2013, about 6 months after us. And what they have is they have a resonator system. It's a 2D system that has resonator, that every 2 neighboring resonators are coupled in 2 channels with a pi phase difference between them. So they engineer the system that has something that like a synthetic magnetic field, gauge field, that behaves in a way that is similar to the model of Duncan Haldane that I talked about. And there were several other propositions. Then there is one that the word topological insulators was not mentioned there. It's by Shanghui Fan. And what he suggested, actually, he suggested to break the backscattering or time reversal symmetry, not by magnetic fields, but by modulation. Okay? In other words, to break it explicitly, by hand, if you wish. Okay? And that is a very interesting paper that was recently realized by Michal Lipson from Cornell, and in silicon photonics platform, actually. So this might have a very good chance to enter industry. And then there was one that I think that is a bit more difficult. It's very nice and conceptual. I was involved in that one too. I gave them some advice on that. And what they suggested, this is a group of Gennady Shvets, is to make birefringence metamaterials that have some particular properties that behave like artificial gauge. So we didn't work with either of these. We were looking for it for several years, and we were thinking, what trick can do the job? And then we had it. Okay, so this is the trick. So if you want to break the back, to make sure that you don't have, that you are immune to scattering or to coupling into the bulk modes, it's easy. All you need to do is make sure that you have a large enough band gap, and then if you have a defect that the variation in the potential is much smaller than the band gap, it will never couple to the bulk. So that's easy. But the trick is how to somehow to avoid the backscattering by the defect. It is something that needs to behave like time reversal, breaking time reversal symmetry. So if you don't use magnetic fields, how can you break time reversal symmetry? So one way to do it is through modulation. So if you think about modulating in time, so unless if you sample your system like a starvoscope every 2 pi, then actually you will not break time reversal symmetry. But if you sample your system at any other time, you do break time reversal symmetry right away by modulation. So let's look at it formally for a minute. So if you have a system, this is the Hamiltonian of the system, and the Hamiltonian is time periodic. You simply modulate your system. So you have some potential, and let's modulate it in time. Okay? So now let's look at how the modes look for an observer that is sitting on the modulating wave. So modulation is sinusoidal. So this is what is called the Fluke modes of this. Okay? So you want to find the energies. So let's start at first of all at 0 frequency. So what you have, you start with an insulator. And now let's put some modulation at some frequency, and let's see what happened. So what happened is that the bands go closer to one another, a little bit. Now let's go to a higher frequency. The bands will go even closer to one another. At sufficiently high frequency, the bands will merge, and if you continue to increase the frequency, they open up, and now you have a topological band gap, in the sense that now you have edge states that cross the band gap from side to side, just like this. So this is at low frequency. You see that the band gap is big, but then when you continue to increase the modulation frequency, at some point they touch, and then for another increase, they open up, and you have edge states that cross like this. This idea was suggested for the first time by Nathaniel Lindner in 2000. His paper appeared in Nature Physics 2011. When he was sick in the hospital, he was a postdoc at Caltech at that time under the supervision of Gil Rafael. And as it so happens, great minds think alike. So a group of other people, among them Erez Berg, Kitagawa, and Mark Radner, at that time they were collaborating with Yevgeny Demler at Harvard, submitted a modest paper to PRB that even though it was submitted a long time after this one, it appeared earlier. Fights with the referees, yes? At that point, still there was no real system to do the experiment. And the one that suggested how to do the experiment is actually my colleague Asa Orbach in condensed matter. So what he suggested is, let us start with a system that is not an insulator, but let's start with graphene. Why? Because graphene does not have band gap. It has intersecting bands. It has the Dirac point. What does it mean? Every little modulation will immediately open a topological band gap. So it will be the easiest to do it in graphene. How to do it in graphene? Well, you take graphene lattice, which is a honeycomb, okay? And now what you do, instead of putting electrodes and modulating, you launch at it a circularly polarized laser field. And circularly polarized laser field will change the potential periodically, just like we said just now. And you open up, this is the dispersion curve, exactly what is expected. Okay, so we heard this in some kind of a departmental retreat where each student had 5 minutes to talk about. So we heard this and said, now we know how to do it. So this is what we went after. So now I need to do a little bit of a sidetrack on that. Let me introduce you to the field of spatial photonics. Okay, just one slide. Let's say that we have some kind of a dielectric material with some changes in the refractive index, and you take a laser beam that is paraaxial and you launch it in some arbitrary direction. Okay, let's call it Z. And you look at what happens in X and Y. Okay, so if your field is time harmonic, you can write it in this way. So there's a plane wave, and on top of that there is an envelope. So under the paraxial approximation, what you find is an equation that looks like this. So if you look carefully at the equation, it has the same structure as the Schrödinger equation. It looks one-to-one, mathematically equivalent. But there are some fundamental differences. In the Schrödinger equation, the evolution of the wave packet is in time. In our case, it's time harmonic. There's only one frequency. So everything that happens here to a wave packet in time will happen here to an optical wave packet, an optical beam, in the Z direction. Okay? So if I examine the propagation, the evolution of my optical beam, as it propagates along Z, at every XY plane, it will mimic exactly the evolution of a quantum wave packet in time as it goes from one plane to another. Okay? So that's similarities and differences. The other one is that because Z is taken, our system is fundamentally has only two transverse dimensions, X and Y. Okay? Evolution is along Z, and you have X and Y. In quantum, it can be 1D, 2D, or 3D. It has implications. For example, what we did 8 years ago, Anderson localization of light. In this system, we have a crossover, but no phase transition. In this system, you can have 1D or 2D, you have only crossover. In 3D, it's possible to have phase transition, at least in principle. Another similarity and difference is the potential here in the Schrödinger equation is replaced by the local change in the refractive index with a negative sign. Why with a negative sign? Because the potential well for electromagnetic wave is a region of higher refractive index. Okay? But other than this, they behave the same, they look the same, so they practically have the same solutions, at least when you talk about mean field, or one particle wave packet. So given that, now we knew what to do. So now we need to take the idea that I just told you about graphene modulating in time, translate it into here, which is exactly what we did. So in other words, what we know, so what we need to do now is to make a system that looks like graphene, a honeycomb lattice that will look like this, okay? And we want to launch the light right here at the edge, and we will see what happens around the edge. And if it is immune to scattering, it will never scatter to the left, and will go around the corners and go around and around. That's the idea, okay? So if I want to look at it from the top, I launch the wave packet here on the surface. If there was some scattering here, it will naturally scatter to the left. But if we do something like modulating in Z, as I will show you, there will not be any states to scatter into, and light will continue and will not be stopped by the corner or defects or whatever. That's the idea. So photonic graphene or photonic honeycomb lattices, we know how to do it. It brings me back to 2006. 2006, it was, at that time already graphene there was a lot of hype around graphene, and we decided we want to make graphene for light. Honeycomb photonic lattice. So what we did there, we created a lattice that looks like this, of waveguides that are at close proximity, and they are organized as a honeycomb. Okay? So if I look at my equation that describes them, this is how it looks. So it looks exactly like the Schrödinger equation. So looking at the evolution of light in the z direction will be exactly like looking at the evolution of the quantum wave packet in graphene, exactly one-to-one. So if I want to look at this, for example, let me see. So I'll take the light and I launch it into some point in the central waveguide. The evolution now of this will be tunneling to the nearest neighbor, next nearest neighbor, and so on and so forth, just like in graphene. Same idea. By the way, I should tell you that when we submitted this paper, which was submitted in the summer of 2006, some of you that know a little bit about Israel will remember what happened in summer of 2006. There was shelling from Lebanon falling very close to the Technion with big rockets. Anyway, so what happened right then, we submitted it there, and we wrote to the editor of PRL that we have photonic honeycomb lattice. We have demonstrated Dirac points and some other features that are very, very interesting. And we said that some of them are features that are similar to graphene, but there are many other features that you can do with electromagnetic waves that do not naturally exist with graphene, for example, effects of nonlinearity. Well, we had mixed reviews, and the editor wanted to reject. So I wrote him a very strong letter and told him, look, this is the first time that anybody realizes the features of a honeycomb lattice outside of graphene where it happens in nature. If you reject this paper, you will bear responsibility to this, because you will see that in 1 or 2 years, there will be many groups that are doing this graphene physics outside of graphene. It will have an impact on cold atoms and on many other systems. And he actually accepted my point and accepted the paper. And if you look now there is a whole field that is called artificial graphene. You do it for electrons, you do it for exciton polaritons, you do it for many things. And many people give talks on this, and sometimes they conveniently forget that we were 2 years or 3 years before anybody else. For example, there is a guy at Stanford that did something like that for electrons. It appeared on the CNN. Hari Manoharan, that was a student when I was a professor at Princeton, and I wrote to him, Hari, I remember you when you were a student. You should give credit to those that did it 3 years before you. But he ignored my message. That's life, huh? So anyway, so now we knew what we need to do, partially, but it's not enough. Now this is, you come to think about it, this is all nice, but graphene by itself, without modulating, is not a topological insulator. Okay, it's on the verge of being a topological insulator, but it is not a topological insulator. There's no topological protection in graphene. We need to do something more. So actually, there is a bigger problem even than that. Let's look at graphene. This is the honeycomb lattice. So the honeycomb lattice has 3 terminations. One of them is called the zigzag, where the atoms look like this. The other one looks like bearded because it has open bonds, like dangling bonds that shoot forward. And this one is the armchair. Why is it an armchair? I don't know. My students think that if you put somebody here, he can lay his hands like that in the armchair. Anyway, this one has edge states. What does it mean? It has states that are confined to the edge, that are localized on the edge, and they are not Bloch modes. They are sitting only on the edge. This one has edge states, but this one does not have edge states. So if you are going to fabricate a honeycomb lattice like this, you are immediately in trouble, not only because of backscattering, but because the armchair termination has no edge states. So if the light is sitting there, it will spread into the bulk right away. So what to do? I can tell you on the hindsight. So how to make topological lattice, I can tell you on the hindsight. So as a separate study, we actually did study the edge states, and that's maybe a good lesson why to do optics, okay? So this was observed in condensed matter. The existence of edge states of this one cannot be observed in condensed matter. Why? Because the bearded edge has open bonds, so it's unstable, and it will always bond to some other material. So my students wanted to probe whether we can see for the first time the edge states here. So I told them, look, it's not important enough because we know they are there. But let's do the experiment. Maybe we'll learn something from it. So the edge state has some dispersion curve. The edge states in graphene, the dispersion is flat. In other words, there is a regime in momentum space where these exist. In the complementary regime, these exist, but they never overlap. So, and we did the experiment, and we found out that there is some interesting artifact, and that the edge states here also appear where they are not supposed to be, in momentum space where only these ones are supposed to exist. So I told them, look, guys, maybe the experiment, there's something fishy there. It smells not so good. So let's check also theoretically. So if you go to tight binding, because solid state is tight binding. That's what people know. So if you go to tight binding, which they did immediately, of course, the theory that was published in the 40s is right. There are no edge states here in that dispersion regime. So what to do? So I told them, guys, go do a simulation of the continuous equation, because the physics is Schrödinger equation, which is continuous. Forget the tight binding, do it, and let's see what happens. And they found out that there's a new edge state. And the reason that the edge state is there, that was never discovered before, there is a very deep reason. If you want to ask, I will explain to you why. And we discovered a new edge state that is universal to all honeycomb lattices. It cannot be observed in graphene because these are open bonds that it's unstable. But for example, in exciton polariton, now they are making honeycombs like that. And in cold atoms, they are making honeycombs like that. So it can be done. Anyway, going back to the topological phase, we are still dealing with the problem, how to do it. So, but we knew how, because Nathaniel Lindner told us in this paper, we need to modulate in time. Remember, for Schrödinger, it's time. Here it's Z, it's the Z direction. So what we need to do is to have a honeycomb lattice of waveguides that look like spirals. They look like this. They are still organized as honeycomb. We have something like 200 by 200, so it's big. So each waveguide, they're all, we have some helicity, which actually breaks the Z reversal or the deflection, the reversal between right and left. So they all have helicity in the same direction and in the same periodicity and the same amplitude. So if you want to write the theory to that, so you do transformation of coordinates, you reach an equation that looks like this. And this A behaves like a gauge field. And what you have here is this is the periodicity of the modulation. This is the amplitude of the modulation. So you really have something that has dispersion curve exactly as predicted. So this is what we are after, only in an organized form as a honeycomb. So let's see from the dispersion curve what happens. So if you are familiar with the dispersion of graphene, this is dispersion curve of graphene. These are the Dirac points. So this is my edge states. These ones are on the zigzag edge, okay? So when there's no modulation at all. And as you see, the edge states that go to the left have exactly the same dispersion as those that go to the right. In other words, there is backscattering in graphene. This is why it's not a topological insulator. But now, let's do this. Okay, let's wiggle the lattice and ask what will happen. So what happens now is that you open a topological band gap. Excuse me. So now what happened is that now the upper edge will have a positive move velocity, and the bottom edge will have negative move velocity. And lo and behold, now what you have is also edge states that are protected from scattering also on the armchair edge. So everything goes around and around. So given this is a nice simulation that shows it. In other words, we have something that goes around. So let's see the simulation. This is the simulation, not tight binding, but actually full continuum simulation. We had a defect here. One waveguide is missing. So the light went by the waveguide, and here it will come to the corner and it will go down. It starts to go down, and this is the armature edge, and it starts to go down further and further, and it will come to this corner and go down. So after doing this, the theory on that and confirming that everything is kosher, we decided to do the experiment. So Alex Tzamait fabricated it for us. And what you see here, these are waveguides that go into the blackboard, and they are helical into the blackboard, okay? So that's the size of a typical lattice that we have. So the lattice constant is 15 microns. So what we do, we launch the light here, and we observe what happened to it at the output, okay? So we launch always the light right here, and we look at it after some distance of 10 centimeters, what happens in the output, okay? And then we shift the input, and we look at the output. So we started here, we launched the light here, and you see the light was already propagating past the first corner. A corner is a big defect. Then we moved it a bit to the left, and light went down. We moved it further and further, and light went further and further down. So what we saw, there's no backscattering. You see there's nothing that came back here. And light was localized on the armature edge that otherwise it would not have been localized. So this was the first evidence. So given this, we decided, OK, let us now do something more dramatic. So we did the same honeycomb lattice with helicity that goes into the blackboard, but now its cut is organized on a circle. It's still honeycomb, but it's organized on a circle. Oh, I'm sorry, on a triangle. So here the edge is a huge defect. So if you launch light on the edge and there's no helicity, what will happen to you is that light will simply stay there because the what is this damn thing? Yeah. So you see, if you launch the light here, because now there's no helicity, this corner on the triangular lattice is a huge defect, so light will stay here forever. And this is exactly what we saw in the experiment when there's no helicity. But now we put some helicity, and what happened to it now is light starts to go to the right. We put further and further helicity. This is 4 microns. This 6 microns radius of helicity. You see at 4 microns already light reached the other corner. At 6 microns it went beyond the other corner. 8 microns it went halfway down. And then to our great surprise, we saw the light going backwards. So instead of continuing, light now went back, and at some point it started to scatter. So what the heck is going on? So it took us some time to understand, but this is what is going on. So when you plot the group velocity, when you plot the group velocity of the edge state as a function of spiraling radius, you'll see that it starts from 0, which means that this is stationary, it's just staying here. Then it starts to increase until it reaches the maximum, which is more or less here. And then it starts to become smaller and smaller until it crosses to the other side. What is going on? So then we understood by looking at the band structure. So that's what happens. So if you look at the dispersion curve, and this is my edge states, and I start now to give it some helicity, so what will happen to it is that at the beginning, you see at the beginning as you increase the radius of helicity, the topological band gap increases more and more and more. Okay, like that, it increases more and more and more, but if you continue to increase the helicity, radius of helicity, oops, no. I want to show it again. If you continue to increase the radius of helicity, then what will happen to it? Here it is. Why doesn't it show? Yeah. If you continue to increase the radius of helicity, at some point the bands collapse onto one another, and when they open up again, the Chern number, which indicates the difference in topology, has gone from 1 to -2. So what happens when they start to come back together again, the group velocity has decreased further and further until it switched sign. Okay, at that point my students wanted to submit it to Nature because we thought that there's a lot at stake. Let's send it out. I told them one more, and this is the one more. I said, now we need to put a defect, just like in the simulation. So we fabricated another lattice with a missing waveguide right here. And we launched the light here, and you can see the light has passed the waveguide and came out on the other side. So now we were happy, and we sent it there. After a short fight with the editors, the paper was accepted by the 2 referees with flying colors, and immediately got published, and we did the first one. So having done that, we said, okay, now let us do some things in optics that will have impact in other areas. Let's do things in optics that have never been explored in condensed matter, not even theoretically. So the first one was nonlinearity. So far, discussion was linear. Okay? But what happens if we put nonlinearity? Nonlinearity, we know how to do business in nonlinearity because we worked on Solitons for many years. And the question that we ask ourselves is the following. Now that we have a topological band gap, can we have solitons in the band gap? In the topological band gap, can we have topological gap solitons? So to solve this problem, actually it's not easy, even mathematically, to find the solitons. If you try to fish them by some kind of a numerical code that you take from the book of numerical recipes, you will definitely fail. But there's a system that I developed when I was young and handsome, and that finds a self-consistency method, which I took the idea from physics, and then later on mathematicians tried to prove convergence and uniqueness, which they never succeeded, but everybody uses it. So we found the solitons, which means that we looked for solitons that in the dispersion curve sit right here. That will show you how we found them. So my student went to the gap, and he found a pretty girl there. Nadia, she looks Iranian, I'm telling you. But he asked her about got solitons, and she didn't know what he's talking about, so he had to solve. And I will not show you, I have a slide that he made that shows the process. It's complicated, but it's accurate. Every single time you find the solution. And then when you run the simulation, you'll actually find that it's a correct one. So we found the solitons in topological band gap. So the idea is now that you launch a strong laser field, not on the edge, but in the bulk. And you ask yourself, can I create a soliton in the bulk? So we found two families. I'm sure that there are more, but the two families are also very interesting by themselves. This is the first one. It looks like a tripod, and this is the second one. And the second one looks like like a hexagon. So if you notice carefully, this one, the energy goes in this direction. The energy here goes in this direction, and this one, the energy goes in this direction. In other words, this one will go with the helicity of the lattice, and this one goes opposite to the helicity of the lattice. Now, why does it happen? Well, because what happens now is that your wave packet creates a defect, and around the defect you have edge states. So here you have like a hill. So the edge states around that hill will be in the same direction, will conform to the direction of helicity of the lattice. But this one, there's no light in the center. So this one creates like a ring, a potential ring. And what we have here, the wave packet populates their inner edge. At the inner edge, the wave packet rotates in direction opposite to the helicity of the lattice. This puzzled us for quite some time, and now the challenge is to do experiments on that. And there's quite a lot at stake because nobody has ever done in experiments nonlinear effects in topological insulators. Having done that, we went further. So until now it was published. From now it starts to be not yet published. So next thing that we were interested is to know if we can store a topological state. Okay, so what does it take to store a topological state? So you have a state, what I didn't tell you is that people in quantum information believe that topological states in topological insulators, because they are protected, they will have longer coherence time, and they'll be very useful for quantum information. So let's put the discussion aside, but it is interesting to know if you have a state, can you store it, and then retrieve it at will. So if you want to store a state, what do you want to do? You want to store it in a stationary state, because otherwise you don't know where to find it. So you want to store it in a state that does not move, that is stationary. And then you want to store it in a localized state. Why? Because if your state is dispersive, then after some distance or some time, it will disperse everywhere. Go collect the pieces of Humpty Dumpty. So the third one is you wish to store it in a protected state, but that is tricky. Why? Because topological states always have non-zero group velocity. So there's a contradiction with number one. But you can store it in the band gap. So because of that, we came up with the idea of looking at the Lieb lattice. Lieb lattice is a square lattice of 3 different atoms. The dispersion curve of the Lieb lattice looks like this. It has just one Dirac cone, not 2, but 1 Dirac cone. Okay? And they are intersected by a flat band. Flat band means that there's no dispersion, and all the states here are localized. So this is an ideal place to store some stuff. Why? Because they are localized. In other words, they are not extended states like Bloch modes. You can create a wave packet that has just 3 sites or 4 sites. Okay? And then there's no dispersion. And when we do this helicity modulation, we modulate it, these bands are affected. The band gap becomes topological, as I said before, but the flat band remains flat band. It's completely unaffected, which makes it ideal. So that's what we did. And I will show you just an interesting simulation of this. So let's say that we have some lattice, And what we do now, we modulate, and then at some point, we stop the modulation. When we stop the modulation, the state freezes, which means that it coupled to the flat band and stays there, and then after that, you retrieve it when you start to modulate again. Next one is something that is now hopefully will be accepted by PRX very soon, and it is about topological transport, topological insulators, and quasi-crystals. Now, quasi-crystals, for those of you that don't know, they are not crystals, and also they are not random. There are more. Okay, it's quasi-crystals were given, were discovered by Danny Shechtman, my colleague from the Technion, and he won the Nobel Prize in 2011. Actually, the first theoretical paper that discovered all the main features of quasi-crystals and also gave the name, coined the term quasi-crystals, were discovered by another colleague of mine, Dov Levin, when he was a student of Paul Steinhardt at that time at UPenn. Nader, I'm not sure that you know, at UPenn at the time. Later on, he became a big name, and he moved to Princeton, and he became a big name and moved to Technion, but not as big as him. Anyway, so what is a quasi-crystal? A quasi-crystal is something that has, crystals or periodic systems, as you can find in Feynman's book. They can have rotational symmetry of 2, 3, 4, and 6, but not 5, not 7, not 8, or not any other number. So in principle, until if you look at Feynman's books, or any other crystallographic book that was written before 1990, you will find that there's no 5-fold symmetry, no 7, no 8, nothing of that. So those are not crystals, and they are not supposed to show you diffraction pattern in the far field, in X-ray diffraction or electronic diffraction. But Danny Shechtman discovered that. And it turns out that what happens there is that you have long-range order, but you don't have local order. In other words, you don't have unit cell. You don't have a cell that you can translate it and have a unit cell. So in the states, they here tend to be fractal state. The states and the dispersion curve is fractal. What does it mean? You can plot a dispersion curve, and then when you zoom in, you see that it's separated to little holes. You zoom in further at little holes. So if you want to count, if I look at the dispersion curve and I want to count the Lebesgue measure of the curve, it's 0. It's full of holes. So the quasi-crystal is a fractal system. It has just holes and nothing more. Okay, so now here all the states in principle are stationary states, including those that are on the surface. So there shouldn't be topological insulators in quasi-crystal whatsoever. But we set up to look for them, and we put this our modulation. I should say on the hindsight that we know how to make them. We did the first nonlinear photonic quasi-crystals in 2006. We know how to make them, and we plot the dispersion curve. What we found out is that this is how it looks. And it turns out that most of the gaps are actually trivial, not topological. But some are topological, and when you take this topological band gap and you zoom in, you find smaller gaps topological and more. So this encircles the region of topological band gaps. And if you want to test the idea, you pick some edge states that dispersion curves are right here, and you launch it in a simulation to see what will happen to it. And that's what will happen to it. You launch it, and you have your system circulating around the circumference. Now, because quasi-crystals are not periodic, you cannot really analyze it using Bloch modes in the usual sense. So you need to start with a finite system. This one has about 200 waveguides, not very many, and you can see that it circulates around the perimeter. And then you increase it to 521. You see they are localized here. And when you continue to increase, they're always localized here, and they are immune to scattering and so forth. So yeah, you see, I knew I have another chapter of I have another chapter of about 6 slides, but I knew that I will run out of time, so I will tell you about it in just words. Okay, so I don't like to conclude, because to conclude means that I should retire and write a book, and I will never do that, either of them. So as a result of that, I will just tell you about some ideas. So I told you already about nonlinearity. To look at nonlinear interactions between topological states is extremely interesting. And it's really, the ideas are there. Some of them have not been explored even theoretically. Very interesting to look at it experimentally, theoretically. Another one is to look at effects of time-dependent effects. It's like magnetic defects. You can use it to generate scattering exactly in points where you want to generate scattering. If it's big enough, it will scatter fully to the other side, to engineer it and so forth. In optics, we can actually do it, and it's interesting, but nobody did. Well, another one is interesting to look at boundaries between 2 counter-rotating zones. So imagine that I have a bulk like this. And I split it in half. both of them rotate, okay, in the same direction, but there's a phase difference between this one and this one. Okay, there is a phase difference. So there is an interface that comes about not because of the helicity, but because of the phase difference in the helicity between the two. It turns out that this can generate a topological state at the interface. Very interesting, we're after that. And maybe these are the most interesting ones. This one is a system that linearly is not a topological insulator. But if you put nonlinearity, you convert it into topological insulator. And this is something that is, now that we know what needs to be done, it can be done in several, not only in photonics, certainly in photonics, but not only. It requires non-local or long-range interactions. So long-range interactions are known also for cold atoms, when you have molecules in the style of what Debye does. And actually, the papers, what it requires is nonlinearity that is really long-range. In optics, we have it in thermo-optical glasses, which have the same mathematics, the same theory, that looks like exactly the husband of Debye did, John Bond, in his first papers on non-local interactions. So it shows, and we are now writing the first theory paper to do that, and we actually know how to do an experiment on that. And maybe I'll say a few words also about these two. This one is, it's an oxymoron. So if you have a system and you put disorder, okay, so what do you expect? So what you expect is to get Anderson localization. I worked on that for quite a few years and so on. But Anderson localization is localized states. They're all stationary. They cannot be topological, yes? So can you have a system that, if it's fully ordered, fully periodic, just like the one I did now, it is not topological at all. But you put disorder, and disorder makes it topological. So how do you do it? So there was a prediction from 2010 by a condensed matter theorist, and it's called the Anderson topological insulator. It has never been done. There's not a single experiment. But we know how to do it now. There was one theory paper from my group last year, and now we already have experimental results. These are the next 6, 7 slides that I wanted to show. And the idea is like this. You take what we did already with the graphene lattice, which is made up of 2 triangular lattices that are shifted, okay? So it's a hexagonic lattice. It's made up of superposition of 2 sublattices. Let's put the mass of the sublattices that will be slightly different. What does it mean? To make the waveguides of slightly different contrast. So what you do, what happens then is that you open a trivial band gap. If the trivial band gap is larger than topological band gap, you've killed your topological insulator completely, in spite of the helicity. But now when you put disorder, what will happen? The disorder will brush away, will close the trivial band gap, and what is left is only the topological band gap. And we've done that, not only in theory, but also experiments. We are now writing the first paper. And last one, maybe I'll talk about the quantum one first. So, for example, what we looked at is path entanglement in topological insulators. And we've shown that if you put defects, if you launch something that is not a topological insulator, either but it has a no gap at all, like graphene, or because it has some disorder that kills it or whatever reason, or it's unbalanced lattices, then what happens is that the coherence, the quantum correlation between them diminishes. So with time and distance, it goes away. But if it's a topological insulator in the style that what I showed you, then the coherence is maintained. It got rejected from PRL because the referees told us, just last week, referees told us, well, it's clear. So maybe it's clear, but I think it's clearly not obvious. And the last one, which is, in my opinion, okay, if you open Nature Physics of this week, and there is a cartoon about the 10 most important discoveries in physics. And number 2 is PT optics, optical PT symmetric systems. These are systems that are not symmetric to parity, are not symmetric to time reversal, but are symmetric to parity and time reversal together. The concept was discovered by 2 good friends of mine, Dimitri Christodoulides, who is the father of the field, and Nimrod Moiseyev, who discovered the exceptional points that are a cardinal issue right there in. So there is a paper that was published several years ago that claims that topological systems must be Hermitian, that they cannot be PT symmetric. In other words, non-Hermitian. So nobody looked at it. But I like this kind of challenges, And we've shown that we can actually find quite a few systems, we can classify them that are non-Hermitian, not only PT7, but non-Hermitian, which means that they have gain and loss. And they're also topological insulators, which means in optics that we can have systems that incorporate loss and gain and still maintain their features of no backscatter and so on and so forth. Thank you very much. This is perhaps the most important comment, that experience reveals that if you think that what I did is important, the most important one is still just beyond the corner.
Moti, thank you. This was a very fascinating talk. Now, the question is the following. You can use photonics and photonic structures to mimic effects from condensed matter, and you can have some very wonderful, very exciting physics. Sometimes, as you have shown, you can have even additional effects in photonics.
No, we can discover new effects that probably cannot be observed in condensed matter.
Exactly.
Or give ideas to people in condensed matter to look for something else.
Yeah, this is true. But the question is, the structures, albeit even if they are not lossy, they are still quite complicated, right? The question is, will they be, I mean, the physics are really fascinating, and you can have very, even new effects that you cannot observe in condensed matter. But are the structures really practical from an application point of view? I'm asking this because we know this, for example, from the field of metamaterials. If you see three-dimensional metamaterials, people also had some very fascinating things. Now they're doing meta-surfaces, they realize it's very difficult to make these structures. So the question is, if you using photonics, you mimic essentially, with some additional effects, of course, condensed matter, fermionic effects, will the structures be practical for applications?
Okay, so very good question, and I will give you, the answer has several folds. So first one is personal. You know, I look for proof of concept. Yes, I was trained as an electrical engineer, but I'm not really a good engineer. So that I go for the new concepts, and I'm sure that I have colleagues or friends or somewhere else that are better engineers than me that will be able to do it. The second part of that, actually, that some of that has already been done in parallel to us by Shangui Fan, because what Shangui Fan did is something that is conceptually similar to us. And it's small, and it's doable on silicon photonics. It's not ideal yet. So what Michal Lipson did is not an exceptional isolator as of this time, but it can be one. So what we did here is really looking at conceptual issues, and I'm sure that there will be other people that will come up on how to make them small, not systems like ours that were really meant to study the physics, but there will be something that goes in, and I think what Shangui did and Michal did is already very promising for applications.
Thank you very much. It was a really very fascinating talk. I make the comparison with experiments done with cold atoms. And it's a field which is developing very fast with the same kind of effect, and it's called quantum simulators.
Yeah.
Would you agree that what you are doing is a classical simulator?
Yes, we do. So far, the experiments that we did are classical, but we are getting exactly into this, because it's not a coincidence that we looked for path entanglement there, because we are after doing here quantum simulators. And I should say regarding quantum simulators, there are several issues there that are really important for an evening discussion, like ones we had. If you want to do a quantum simulator that will look at the linear, non-interacting effects, optics will always win, always. If you want to do something that is mean field, quantum simulator, let's say the Gross-Pitaevsky equation, optics will always win, through nonlinear optics. But if you want to go into quantum any-body, that is something that optics suffers greatly, because the interaction between two photons through a mediator of one or few atoms is extremely weak. This is why people do highly excited Rydberg states or excellent polariton condensates or all kind of other tricks to do that. So the pioneering one was what you did and others on a cavity QED, and Jeff Kimball. And Jeff Kimball now is doing photonic crystals and everything in photonic exactly for this reason. So everything that has to do with non-interacting system, including boson sampling, is a kind of, it's a linear system, but it can be interpreted as kind of interactions that in optics we will always win against cold atoms. But if you want to talk about, let's say, many body localization, like what Immanuel Bloch did just now, this is something that we will always lose in my system, maybe in Rydberg states. So on that note, I can tell you that part of what Immanuel is doing now is exactly along these lines. How do I know? We have a proposal together So I know exactly Immanuel Bloch. And the other one, the other part of that is that people that are doing Rydberg states today are exactly on our heels, exactly that. Ofer Furstenberg, who was a postdoc with Misha Lukin, is exactly doing this. So within 3 years, they will do Fluke topological insulators with light, many body. And yes, we are doing quantum simulators, of course. But I think Karim was there. He also wanted to ask something.
We'll take 2 questions, 1 and then 2.
Yeah.
The question is, what determines how large the defect can be for it to go around, and what determines that size?
Okay.
In this case?
Very interesting. So the answer to that is not conceptual. It has to do with the fact that when you put helicity, okay, then you inevitably couple to radiation modes. You know, you take a waveguide and modulate it or twist it, you will lose light to leaky modes. So we are limited by propagation distance. So the maximum that we are able to go in our system is to go around 2 corners. But it's not conceptual. This is where fabrication restrictions are there today in our system, in a system like ours. I'm sure that it can be. So we are already looking at other materials, like in silicon. We have starting to do experiments now, and also in chalcogenides. And the reason for chalcogenides is because the nonlinear effects are very strong. So if you ask me, we will probably be able to go and complete 1 circle, but not more.
Fantastic talk, really, I enjoyed. So one thing that I have seen in your simulations of solid state case with light was a scalar Schrödinger equation. So the point is that light gives you, if you include polarization,
Sure.
Gives you the possibility also to exhibit or simulate something more interesting, for example, like Rashba Hamiltonian, including something like Pauli or Dirac Schrödinger equation, something like that. So are you thinking about going to that direction?
Yes. So we have a paper under review on Rashba effect. But I can tell you like this. First of all, if I may, I would record you and play you to my self-important colleagues. Because, you know, somehow people in physics are fascinated by Schrödinger equation. And they forget that Maxwell equations are deeper and more interesting. If nothing else, because they have tensorial effects in them. They are much richer. So yes, it is extremely interesting. And I can tell you that usually we go, first of all, after the scalar effects. But there's a lot to say there. If you go, this is a complicated system, but if you go to simpler systems, for example, if you think about 3D localization of light, Anderson localization of light, and you look, and your material is completely homogeneous, but you include vectorial effects that in 3D are inevitable, you will see that you have new physics, and it's richer. And I can tell you that there is also localization there, and it offers new features. So definitely yes, and unfortunately people like to look at the simpler case, you know, and say, then the rest it's for the engineers that do electromagnetism. It's no, everything is known, it's in Maxwell equations. So yes, it is very interesting to go there, and we are going to part of it, and I'm sure that there will be others that will follow.